on best practices for feed water control for boilers, especially as it relates to the options that one has for pipe and pump control, for piping, I should say, and pump control, because some ways may be a little bit better than others when it comes to, not only maintaining proper level control in the boiler, but also saving energy. So this is what we're going to be covering today. We're going to take a look again, address the high-pressure boilers that we looked at last month, the fire tube and the industrial water tube, in the size range of 100 to 1,200 horsepower. That seems to be the sweet spot for the market today in terms of the most units sold in that size range. Where the water level is measured in these boilers, we want to discuss that, make sure that you understand that, and the ways in which the pressure in the boiler and the system is controlled. And also maintaining a reliable and safe level of water in the boiler is critical, and I'll show you some dramatic pictures of why I'm saying that. Ways in which the boiler water level is controlled, we'll talk about that. And then matching this control with 4 distinct pumping strategies that Jim will be getting into, and a couple of pump selection exercises. We did that last month. It seemed to be very well accepted. People enjoyed that, so we'll do that again. And then, of course, as we normally do, we'll give you a summary of at least the takeaways that Jim and I think are the most important for you to go away from this program with. And then, as normal, we will end with a live Q&A, as much questions as we possibly can take with the time allotted. All right, as I mentioned, I just wanted to reflect back to last month in Part 1 when we discussed some boiler feed equipment basics and pump sizing criteria and the selection. And said at that time that we would be concentrating on these types of boilers as they are the most commonly used when referring to boilers spanning a size range of between 500 and 1,200 horsepower. And, of course, design pressures, as I mentioned before, 150 to 500-pound design. Again, it's the fire tube and industrial water tube boilers which are most commonly specified and applied in these areas of operation. Starting then with the industrial water tube, also known as the IWT, you'll recall how the pressure vessel is basically constructed with the water-filled tubes emanating from the lower mud drum, as we call it, and connecting to the upper steam drum where the mix of steam and water are discharged. Now, looking at the steam drum in this industrial water tube boiler more closely, you see the approximate water level that we need to maintain in order to provide safe and reliable service. And also note the steam disengaging or the steam storage area where the steam accumulates as the evaporation of the water takes place. And then once the steam is formed, it then exits through the steam outlet to the connected steam header, which then leads to the process and or the heating load in the facility. And then we have the fire tube boiler. And as noted last month, different from the water tube boiler, in that the flame and the hot gases are in the tubes and the water surrounds them, as you can see in this picture. But what is important for today's discussion is again noting the critical water level that we need to maintain and the steam space, that area along or just below the outlet connection, which then leads to the steam system, the piping. So, in essence, what this all means is the water coming into the boiler is evaporated as it reaches its saturation point based on the operating pressure. More BTUs are then added by the burner, and the liquid changes phase and becomes a gas, which is known as steam. So the water level in the boiler is a critical dimension as it not only provides the substance for the steam to be created, but also provides the assurance the boiler doesn't experience an overheating condition where the boiler tubes and furnace are compromised, causing a rupture when a significant amount of the water in the boiler suddenly expands 1,600 times the tremendous force ripping the boiler from its moorings and tearing it from its piping connections, sending, in this case, a 65,000-pound monster out of the building, and at the same time, this 10,000-pound rear door is torn loose, exiting the rear wall of the boiler room, but while it's on its way, also taking out the deaerator. So, needless to say, the safety devices on the boiler are very important, especially those which are responsible for sensing the overpressure conditions and those responsible for getting the proper amount of water in the boiler at the proper time and then shutting it off when the level in the boiler gets too low. And those controls I'm referring to start right here with the operating control, which turns the burner on when the load demands it and shuts it off when the load is satisfied. The high limit control is a manual reset device, and it shuts the burner off if the operating limit control fails. Now, the modulating control, seen there on the right, varies the burner's input based on a varying load demand, cycling from low to high fire and various points in between, depending on the burner's turn-down ratio. Or the modulating control, rather than being mounted on the boiler, could be mounted in the steam header as shown here, giving a more anticipated signal of what is going on in the process. Or maybe this is a transducer sending a 4 to 20 milliamp signal. And that could be going to a plant master, which is controlling several boilers required to meet a rather large load or maybe a large varying load. So the boiler controls today are advancing to the degree of increased flexibility and sophistication for sure. And as such, so is the way we feed water into the boiler, taking advantage of the technological advances and applying them to not only provide safety, but reliability and system optimization as well. All right, let's start the boiler feed prompting device discussion with this control. Many of you, I'm sure, have seen many times. It's the old standby, the McDonnell-Miller low water cutoff and pump control, which was a standard in the industry for many, many years and is still used quite extensively today. Now, if we look at the cutaway, you'll see the construction, including the float bowl, which contains the boiler water. A float connected to the armature, which is connected to the switching head. Now, here's a closer look at the switching head. And as you can see, we have two choices, either mercury-filled switches or snap-acting. Now, these were introduced to snap-acting a number of years ago because of the concerns of mercury getting into the groundwater when the controls were discarded into landfill sites. Well, anyway, the result is the same. As the water level in the boiler shell or drum drops to a certain point, and before the low water cutoff point, the switch makes and the pump is started. Now, this would be a situation which Jim will be discussing later, wherein the feed pump strategy is an on-off operation. Oh, and by the way, before going any further, I also wanted to mention that regardless of what low water cutoff and pump control option one chooses, of which there are many choices, it has to be mounted specifically and accurately so as to reflect the actual level of water in the boiler's shell or drum. Now, here you see it mounted on a fire tube boiler with specific mounting dimensions for ASME Section 1 of the code, and that would be, of course, in the case of high-pressure steam boilers, Section 1. Note, we want 2 inches above the top layer of tubes at the first visible point in the gauge glass. Very important, as we certainly don't want anything to happen, as I showed you just a minute or two ago. Now, I just mentioned advancing technologies and other low water cutoff and pump control options out there, and the one that you're looking at now is retrofitable, as you can see, and is gaining considerable popularity in the industry, and that's the magneto-strictive technology. Now, actually, the concept has been around for many years, but only fairly recently has it been applied to boilers. Now, looking more closely at its inner workings, we actually find a multifunctional level and pump control which incorporates both digital and analog output signals, which I'll discuss next. But firstly, to accomplish this multifunctionality, you find the sensing rod constructed of red brass and containing an embedded wire, which is constantly and electrically sensing the titanium float as it moves up and down, thereby reflecting the precise water level in the boiler. And then you have the electronics housed in the sensor head, which besides sending the digital and analog signals is also sending the level and alarming signals, both high and low water alarms, to the display box mounted just adjacent to the level control on the boiler. Now, I just mentioned how this control sends both a digital signal for starting and stopping an on-off pump, or starting with initially a continuously operating pump. And it normally has two analog signals, let's say 4 to 20 milliamp, and sending those signals to a loop controller or a PLC for the purpose of indicating level in the boiler and operating a modulating feed water valve. Now, looking at the pictorial drawing in the upper right corner of the screen now, you see how the pump and the feed water valve are typically configured. And Jim will talk more about this a bit later. I also wanted to mention that this technology can be applied to variable speed feed pumps and modulating feed water valves too. That combination. Now, in this case, we need to install a pressure transducer between the discharge side of the pump and the feed valve. And as the feed valve modulates from open to closed position, the signal from the transducer varies and is sent to the VFD controller, increasing or decreasing the motor's speed. Or there is another option that Jim will be discussing shortly, and that is eliminating the feed valve altogether and just use the 4 to 20 milliamp signal from the level control and then send it directly to the VFD drive. Now, there's one last thing that I wanted to briefly review with you before turning the reins over to Jim, and that is the three-element feed water control. Now, this is normally applied to critical process loads and industrial water tube boilers, where very precise level control is very important in avoiding wet steam and boiler outages. The concept involves three interrelated elements: water level, steam flow, and feed water flow. Now, looking at the diagram on the screen now, you see the red arrows pointing to the respective elements. The level control is normally a standard level control with a loop controller indicating the level in the steam drum. And then you have another loop controller receiving a signal from a pressure transducer, or it could be a flow transmitter mounted in the header, similar to what is shown, I showed you earlier in that piping diagram. Now, this is an anticipatory control or feed-forward control, which sends a signal to the feed water regulation valve if a sudden drop or increase in pressure or flow is sensed, indicating a process load increase or drop, and thereby adjusting the flow of the feed water, even if the drum level is within expected tolerance. So it's an anticipatory control strategy. And finally, you have the third element, the feed water sensing device. Again, probably a loop control working in conjunction with the level and steam element loops, and it's sensing a drop or increase in feed water supply pressure, but then intervenes in the adjustment of the feed water valve accordingly. And in this case, the feed water control becomes the master, and the level and steam loops are subordinate to it. These systems, of course, they have to be properly set up and adjusted in the field by a qualified technician based on the operating conditions within the plant. But once they're set up, they do control the feed water flow to the boiler very, very well. Okay, enough of me with the preliminaries for this discussion today, covering the various ways pumps are initially signaled and the type of devices they are working with. Now here's my associate Jim Sweeteye with the specifics on the various pumping methods that are most commonly applied. Jim?
Well, thank you very much, Steve, and thanks to our attendees for coming today. Steve, I think that presentation sets up very well what I'm about to show you relative to the controls for the feed pumps themselves. We have 4 different control methods that we encounter in these systems. There's simple on-off control with a fixed speed pump, and that's the old way of doing it, still done today. Feed control valve, which Steve mentioned, and a fixed speed pump. Then we can get a little bit more advanced and go with the feed control valve with a variable speed pump. And finally, the latest way to do this was with a variable speed pump only and with no control valve. And we'll show you what the relative advantages and disadvantages of each of these are, so you can use that information to help you make decisions for the system you're working on. So here's the first control method. It's simple on-off control. The control box is responding to level in the boiler to cause the pumps to turn on and turn off according to the need. That sensor is mounted on the boiler, which Steve mentioned. Could be float-actuated set of switches, like Steve showed you. I mentioned these are fixed speed, and they are intermittent duty pumps, so they will turn on and off. When the water level falls to that pump-on level, the pump starts moving a large quantity of relatively cool water into the boiler. When the pump-off level is reached, the sensor causes that pump to stop. Now notice, there's no bypass line going from the discharge of the pumps back to that deaerator tank. And there's also no feed valve between the pumps and the boiler. We're going to show you a couple of selection exercises in this webinar series, and we will not be showing you selection on this one since it's kind of the standard way. What you'll see with the other methods would prepare you to select a pump for that particular control method. Now, there are some advantages and there are some disadvantages to this simple on-off control. It's inexpensive, it's very simple. There's no bypass valve, which, you could argue wastes flow, and there's no feed valve. And there's pretty significant pressure drop across the feed valve, and, pressure for a pump equates to energy consumption. The higher the pressure loss in the system, the greater the horsepower required, the more kilowatts, and that results in higher energy consumption and higher costs for power. But there's some disadvantages, that offset this simplicity. The stresses on the boiler. The pumps have to operate across a pretty wide range on their curve, and they can encounter situations where they'll cavitate, and that's really hard on the pump. Large number of starts and stops, like it says, can stress the pumps and the motors. Number of starts and stops per hour can vary, but it can range in that 6 or 8 starts and stops per hour. You get variations in steam production, and there's something called boiler water swell and carryover. And basically what that is when water gets mixed in with the steam that goes out into the distribution system, and when that happens, bad things happen in the system, as Steve indicated earlier. Okay, now let's take a look at the second method. Now, there's a feed valve that we've introduced here if you look in the lower right-hand corner, and that feed valve opening and closing is also controlled by a level sensor on the boiler. That feed valve controls the water intake from these fixed-speed pumps. And, of course, the intake is adjusted according to the steam production. But this method requires that instead of having intermittent duty pumps, they have to be continuous operation. So we have a bypass line that goes back to the deaerator tank. You can see that going from the discharge header. It could be a vented feed tank in addition to a deaerator, by the way. It could be either or. So there's a bypass line. So the selection exercise that we did in the previous webinar, and if you didn't see that webinar, I would encourage you to go watch it. We did a selection exercise based on this control method. And you can go to the Cleaver Brooks training site to watch a recording of that. There's some advantages and disadvantages to this method as well. Advantages, that carryover or swell that we talked about earlier can be minimized. We do have the feed water adjusted according to the steam consumption. And the quality of steam is higher because we have a more constant water level. It's not constantly jockeying up and down to such a great extent. But disadvantages, there's that bypass, that wastes flow. Feed valves are expensive. They have to be maintained, and you also lose a lot of pressure across them. So those are some of the challenges. Let's now take a look at the third method. Now, we've still got a feed valve, and we've still got a recirculation line, but these are variable speed pumps. We're still controlling the water level in the boiler with that feed valve, and that's being controlled, its position is being controlled by a level sensor in the boiler. We're using a variable speed pump here, like I mentioned. This method also requires that the pump is set to continuous operation. So we, again, have that bypass line from the pump back to the deaerator tank or a vented tank for when the boiler's not calling for water, or when the water that's being called for is a low rate, because that puts the pump too close to the deadhead. Often this pump's controlled with a constant pressure mode. So as the water level sensor on the boiler indicates this raising and lower of water in the boiler, then the sensor sends that 4 to 20 milliamp signal that Steve mentioned, sends it to the feed valve, and there's some preset parameters. The feed valve modulates towards a more open or more closed position, depending on that need for flow. Now, notice that the sensor, neither the sensor nor the feed valve, is sending an electronic signal to the feed pump controller in the drive. Instead, there's another method for doing that with a transducer that's located between the pump and the feed valve, and that's actually, that sensing of pressure change is what provides the impetus for varying the motor speed. And that drive, the signal goes to the drive, that sends the signal and causes the pump and motor to speed up or slow down to meet those change in flow requirements while trying to maintain a constant pressure. And we're going to use this control method for one of our selection exercises in today's webinar. Okay, advantages, disadvantages, that swell and carryover is minimized. There's some savings on pump operation, and the steam quality, again, can be higher than some of the other control methods. But there's a bypass on the disadvantage side in the feed valve. We've mentioned those both chew up energy. The pressure loss across the feed valve does often require a larger size pump, and then you've got the addition of a transducer in your system. So there's some pros and cons to each of these methods. Just a quick word on another device that can be used with that particular control method. In those conventionally designed systems, we had an orifice recirculation line. And it doesn't matter whether it's for a fixed or a variable speed pump. When you've got that recirc line, there's always return flow to the feed tank. And that happens, importantly, even when the pump is running at its duty point, which is at low head and it's far away from deadheading. But you're still getting constant recirculation flow when it's not really needed, and that amounts to wasted energy. So one way you can get around that is by installing this auto valve in the recirculation line. The way this works, you can see the pumps located off to the right. And the idea behind this valve, it's closed completely whenever the pump is operating in an allowable flow range. But when the demand for steam drops, and that feed water valve modulates to a more closed position, pump starts getting close to deadhead, that's when the auto valve opens, and it allows water to flow back through that orifice to the feed tank or a deaerator. So there's recirculation flow only when you need it, not when you don't need it, and that results in reduced energy wastage. And in some cases, this may even allow a slightly smaller sized pump, which would be an additional advantage. Okay, method number 4, final one, is a variable speed pump, less a feed valve, and less a recirculation line. The water level in the boiler is being directly controlled with this variable speed pump without the use of the feed valve. Notice there's none in that line in the header going to the boiler. These are continuous duty pumps. They're controlled by a level sensor on the boiler directly. So the water intake is controlled directly according to steam consumption. And in addition to the fact that there's no feed valve, which adds a lot of head to the system, the bypass line's been eliminated, which eliminates wastage of flow. And we're going to be using this control method in one of the selection exercises today also. Like anything else, there's advantages and disadvantages. The feed's adjusted according to steam. That's good. Even steam production. Faster reaction time with change speeds. That's good. There will definitely be energy savings on pump operation, and we'll demonstrate that to you in our exercise. You get rid of the bypass line and the feed valve, and of course, the swell and carryover risk is minimized. But some disadvantages. This is a more sophisticated control, and it does require some very qualified startup. You have to have a technician that really understands what's going on here. You do have to put a check valve, non-return valve in the line. And we won't go into too much detail on this, but there has to be a minimum frequency defined to ensure that that pump can always overcome the pressure in the boiler. But the pump has to be capable of stopping when steam consumption is at zero. So it takes some skilled technicians to set this thing up and get it up and running properly. Okay, so there's our summary of our control methods. We've got a couple of fixed speed solutions, a couple of variable speed solutions. Some that, the first one's intermittent duty. The rest of these are continuous. Some require feed valves, some don't. Some have recirculation lines, some don't. And all of this has a pretty significant impact on the boiler feed pump equipment that gets selected at the end of the day. We have provided for you a checklist when you're selecting a boiler feed pump, and this is available as a handout later. You can follow these steps to make sure you don't miss anything in the process of selecting that boiler feed pump. Okay, there's also a sheet that you can get later as a download that has some useful formulas so you don't have to go hunting for them. That's handy. For this selection exercise, here's the specification we're going to follow. We're not going to read these off one at a time. I'll refer to these points as we walk through the selection exercise. But later, if you want to go back and watch a recording of this, then you could check out each of these points and work through the exercise on your own. Okay, so here is last webinar, which was a month ago at the end of July. We did a selection exercise based on this fixed speed pump with a feed valve and a recirculation line like shown here. Remember, this is continuous operation, so that requires the recirc line back to the DA tank when the reduced volume of water being called for. So there's continuous flow even when that feed valve's completely open and the boiler water level needs to rise. That was what we did last time, and we're going to select another pump this time, and then we'll compare results in the two so you can see some advantages to each method. Okay, so what we're going to do now is select a pump using this variable speed pump and motor instead of fixed speed. It's also going to be continuous duty, so there will be a bypass line just like last time, and there's also a feed valve just like last time. Note that we've added a pressure transducer between the feed valve and the pumps. Oops. Yeah, you can see the transducer there. as the level sensor in the boiler senses that raising and lowering of water level, it sends perhaps a 4 to 20 milliamp signal to the feed valve. That causes it to modulate more open or more closed. And that allows more or less water to flow from the pump to the boiler. The transducer senses that change in back pressure from the modulating feed valve, and it sends its 4 to 20 milliamp or some other signal to the controller for the drive, the variable speed drive, and that causes the pump and the motor to speed up or slow down to match the flow output to the actual steam demand and the water level in the boiler. So I'm going to jump through some of the steps in this, and we're going to go right to this performance curve. As in the previous exercise, this pump requires exactly the same 28 gallons at 272 feet, and we find that an 11-stage pump meets the conditions of service. And we're jumping through this exercise quickly because we're going to dwell on the next one in a little bit more depth. So yes, that 11-stage pump met our need. Here we can do some comparison. Exactly the same pump and motor models as used in the previous one, except this one has a variable speed drive. The previous one was for fixed speed. In both cases, we had to use feed valves and recirculation line. And that means that based on the process for selection, they both require the same flow and head characteristics. So we can use the same 1.25 inch suction and discharge pump, 11 stages. They both operate at the duty point, in other words, full flow, at 65% pump efficiency. And both of them put a brake horsepower load on the motor of 2.96, almost 3 horsepower. So if they both give exactly the same performance at that design duty point, why would you want to spend more money on a variable speed unit? Why not just buy the fixed speed unit and forget it? And after all, the control mode with the fixed speed motor is the most commonly installed type. So why not just stay with that? Well, there's a few good reasons. And the most important one of those is probably that the variable speed unit is going to consume less overall power. Because remember, as that feed valve modulates closed, and that's a lot of the time, the head on the fixed speed pump rises at a certain amount of reduced flow is passed. And a lot of that head just equates to wasted energy. The feed valve modulates closed on the variable speed pump, and it reduces its head output automatically. That's the beauty of variable speed. It reduces its head output automatically. And depending on the application, that could be 30, 40, 50% or even more reduction in head. And if you've ever taken a pump basics course, you'll know that there's a almost direct relationship between head reduction and power savings. But remember, the variable speed unit is going to be more expensive in the initial purchase price. So you need to perform a life cycle cost calculation before making your final decision. Let's take a look at what's going on with the curves. Both of them, when we're calling for full steam, are calling for 28 gallons per minute at 272 feet, as you can see here. And both of them, if you look at the lower part of this curve, which is the horsepower curve, they're calling for just about 3 horsepower. So what's the difference? Well, the difference is when the valve modulates closed, we have reduced flow. On the curve on the left, for a fixed speed pump, take a look at those blue arrows. As we work back to a lower flow, perhaps at 18 gallons a minute. You can see where the blue arrows are. With the fixed speed pump, we move up and to left on that curve to about 325 feet. And that gives us a load of just under 2.4 brake horsepower when we adjust for specific gravity and some other factors. The variable speed pump on the right, using this pressure control, and we're using the red arrows, we don't operate on the black curve line. We operate on that magenta line. So as the flow is reduced to 18 gallons a minute, perhaps, the head is reduced. Instead of being 325 feet, it's only 272 feet. And that gives us a load down at that point of only about 1.9 brake horsepower, significantly less than the 2.4 with the other method. So, as the variable speed pump modulates at reduced flow, there's also reduced head, and that adds up the power savings. And the lower the modulated flow, by the way, the greater savings. So, you need a load profile on how your boiler will actually operate. And that's one of the major benefits of a fixed speed pump. Okay, now we're going to, again, there's your checklist. We're going to quickly do one more exercise and do a comparison and show you what kind of results we get with the fourth control method. There are your useful formulas. Again, here's our exercise. And I'll use these, and we're going to go into a little bit more depth in this particular exercise. As you can see here, we're using a variable speed pump without feed valve. There's a sensor on the boiler, and that's directly feeding data to the control on the drive, the variable speed drive, to speed and slow down the pump to match the flow rate to the needed water level in the boiler. There's no feed valve. That adds a lot of head to the system, so getting rid of that is good. And there's also no bypass line. Both of those are going to help in reducing costs and power consumption. And there's additional variable speed benefits of power consumption, as you're going to see here in just a minute. So as we did last time, we use this process to check off each of the steps as we go. I'll probably check off about every fifth one in the interest of time here. So first one is determine what control method we're going to use. Well, we're going to use a variable speed pump with no feed valve and no recirc line. We picked that up from the specification. So first thing we need to do is to calculate the base flow rate. And we calculate that base flow rate using this formula. The boiler horsepower times a 0.069 times a factor, which is C. That C factor varies. It is 1.15 for continuous duty, and it's much higher for the intermittent duty. So we do the math here, and it comes out to 20 gallons per minute. That's our base flow rate. Now we have to add to that. If we have to add for continuous boiler blowdown flow, which was explained in some detail in the first webinar, we have a base flow rate of 20. If we need to add bypass flow, which we're not going to in this case, that would add even more. The blowdown flow, this continuous boiler blowdown flow, to get rid of total dissolved solids, it's usually about 10% of the pump's flow at the best efficiency point. So, we need somewhere around 2-3 gallons per minute. And that value, by the way, will be set by the water treatment people. There's no recirculation bypass flow. That's for step number 4, so we don't have to calculate for that. Next, we have to calculate the total flow, and we simply take the base flow of 20 plus the blowdown flow of 3. There's 0 gallons per minute of recirc required, so our total flow is 23. Do you remember on the previous exercise we had 28 gallons per minute? So right off the bat we're saving water, and really that equates to saving of energy. And that was required in both, that 28 gallons was required in both previous exercises for the other control modes. Okay, so we can proceed to the next step. We have to calculate the base pumping head. We have to take the boiler operating pressure plus 3%, and there's a formula that we have to follow, taking the base head and multiplying the pressure of 100 psi times 2.31 to convert to feet, times a 1.03 safety pressure setting, and then we divide that by specific gravity. That all comes out to 250 feet of head. Next, we have to take a look at all of the head add factors that influence the head in the suction piping system. You know, the gauge pressure on the DA tanks, water level elevations, and some friction losses. And in this case, that all comes up to 20 feet. So we can check that item off our list. Then we have to add for the friction loss through the discharge piping system. And it's only 7 feet here. There's some friction loss, a little bit of elevation we have to worry about. But notice there's no feed valve. And that feed valve at 15 or 20 psi can add 30 to 40 feet of head to your system, which gives you quite a bit of additional head, and that's power consumption. So we could add them up, 250 feet plus minus the 20 feet because we've actually got some factors working in our favor there, and then plus the 7 feet of friction head on the discharge side gives us 237 feet. Now you might recall in the previous exercises the head calculation was 272 feet. That was primarily because of the feed valve, so you can see the advantage here of elimination of the feed valve through the use of direct control of a variable speed pump. All right, then we have to worry about our pressure safety valve settings. The pump has to be capable of achieving a shutoff head or a dead head according to this formula that's defined in the standards. We have to be 3% above that boiler safety valve setting. The spec tells us that that setting was 115 psi, so we do this math, and what we learn is that in addition to achieving that 237 feet at the design flow rate of 23 gallons per minute, the pump also has to be capable of achieving 287 feet at deadhead. A very important calculation that we have to make. Next, we need to worry about the temperature in the source tank. In this case, we're using a deaerator tank at 227 degrees F. This helps us in making an NPSH calculation. Net positive suction head available, and that's a source of another course if you'd like to come to one of those. We take our elevation on our suction side. We do some math with the absolute pressure and the vapor pressure. We subtract some suction line friction, and we find out how much net positive suction head available is forcing water into the eye of the impeller. And in this case, it's 8 feet. That's the value we have to be able to deal with. All right, so we review all the curves that are available, and we find this 9-stage pump that meets the flow and duty points. Now, do you remember on the previous 2 selections we had an 11-stage pump? So right off the bat, we have a smaller pump. That saves money. Now, in the previous exercise, we used a variable speed pump also when we were operating against a feed valve. And in that situation, we had significant energy savings. And because with this exercise's variable speed pump, we're going to experience similar energy consumption reductions at those lower flows. So once again, we have that benefit. At lower flows, lower power consumption. And you need to run a load profile on your anticipated boiler operation to determine just exactly how that load profile can be translated into energy savings. Okay. So, yes, we discovered that 9-stage pump can do the job. What about that pressure safety valve consideration? Can we meet the deadhead with this pump? It required 237 feet, or in the middle of the curve, at 23 gallons a minute. But back at 287 feet, what does the pump do? Well, we're okay because the pump can achieve 289 feet. So it's a couple feet higher than the safety valve setting, and that's good. So the pump meets that criteria. Next, we have to take a look at the net positive suction head. Our flow, remember, is at 23 gallons a minute, which I've indicated by these red arrows. In the conventional impeller design, which is that dashed line down at the bottom, we need to figure out what our net positive suction head required is by the pump, and then we have to add 2 to 4 feet to that. And we're coming in at, what is it, about 5 feet. So if we added 2 feet to that, that would give us 7, and that would be less than the 8 feet available. So that would be okay, but we always should be conservative. You could get yourself into trouble, so we should add the full 4 feet of safety allowance, which means you'd have something like 9 feet required. And that's a red flag. You really need to consider going to the low NPSH design, which is indicated by that lower solid black line where we have, about 3.5 feet of NPSHR. When you add the full 4 feet of conservative safety factor to that, we still only have 7.5 feet required. It's less than the 8 available, and that pump should not experience cavitation at the duty point. Okay. So we determined that there's the math on all of that, which you can take a look at later, and that pump does meet our requirement. We can tick that off the list because the requirement is less than the available. Just a couple more steps here. We have to check material compatibility according to that process checklist. We were specified with 316 stainless pump materials and the mechanical seal materials, as you can see here. And the pump manufacturer confirms that, yes, that pump is available in those materials, so it meets the specification. So then, as the last step, you just want to tick off the last item, go back and check all of your calculations, make sure you've got the right pump, tick it off the list, and you've got a good pump that will meet the requirements. So we'll just take a quick look at all 3 exercises. The one from last month, number 2 was we did an abbreviated selection on today, and then number 3 is the one we went a little bit deeper into it. You can see which ones are fixed and variable speed, which take feed valves and recirc lines. And note how the flow and the head are lower for that variable speed controlled pump when the feed valve and the recirc line are not required. Now, these are all the same 1 1/4 inch by 1 1/4 inch pumps, but number 3 uses only 9 stages versus 11 for the former 2. Now, the duty point efficiency is slightly lower on the 9-stage than on the 11-stage pump. But when you run the calculation, the total brake horsepower load for number 3 is significantly lower than numbers 1 and 2 because there's less flow and less head required. And in some applications, that can actually allow you to purchase a smaller motor, which is a further upfront cost reduction. So you can see what the advantages are to the variable speed control method when those feed valves and recirc lines are eliminated. And better steam quality is certainly one of the chief reasons. Service and repair costs on the feed valves go away. And because the pump operates usually well below 23 gallon a minute duty point, remember it goes back towards the left-hand side of the curve, where with our proportional pressure control, we have reduced head and reduced power consumption. So if you recall, in the 2 curves we showed you earlier when we compared fixed speed and variable speed with feed valves and recircular lines, you get the same variable speed benefits back at those low flows with this 3rd selection example. Now, if there's a downside to that latter choice, to number 3, it's because it does require the involvement of an experienced field technician. So you need to run complete life cycle cost analysis. Finally, and that does wrap up our exercise, there's additional training available from both Cleaver Brooks and from Grundfos. The Grundfos site, which is shown here, has various virtual courses and webinars, and PDHs and CEUs are available with many of them. So with that, I'm going to turn this back to Steve. Thank you very much for your attention, everyone.
Very much. I just want to go through a quick summary of what we covered today, at least our major takeaways. The low water cutoff and pump control is the most important safety device on the boiler, and I think I showed you why. It controls the safe level of water in the boiler and shuts it down when the level drops to an unsafe level. The level control may include a float with switches or other electronic devices, providing safe monitoring and pump and/or modulating feedwater control. These electronic level controls can work in conjunction with VFDs, as Jim was pointing out. Three-element feedwater control involves the interrelationship of level, steam flow, and feedwater flow. With on-off pump control, the signal comes from the low-water cutoff, and there is no modulating feedwater valve or a bypass line. Continuous running pump strategy with the modulating feedwater valve includes a bypass to ensure proper operation, and it may add to the size of the pump, as Jim explained. A continuous running pump with variable frequency drive and modulating feedwater valve also requires a bypass line to compensate for no or low flow conditions. With this strategy, the signal from the modulating feedwater valve normally comes from the level control, and a separate loop controller is used for the VFD. With the auto valve in the bypass line, the recirc stops when full flow conditions exist, saving pump energy and possibly resulting in a smaller pump size. With the variable frequency drive and no modulating feedwater valve, the recirc line is eliminated, resulting in a smaller pump selection. And this strategy requires an expert technician for commissioning. I think that Jim emphasized that correctly. So it's now time for questions. We're running a little late, later than we normally do, and I will want to hasten to add here that all of the questions that came in during this presentation, and while we're answering the few questions that have come in, every single one of them will be posted and answered on our website in a couple of days after this presentation. So with that, let's hear from Susan again on some of the questions that were